So indeed, I think the topic of what I want to talk about, I think actually fits in an actual way with the effective field theory story, and not so much as being anything wrong with the effective theory. In fact, it's as useful as ever. The question is whether or not there are kind of warning signs about what looks okay from field theory is actually okay or not. In other words, it will put some kind of a damper about what we think about effective field theory and its applicability. So let's start. So quantum field theories without gravity are well understood, and they are beautifully described, by path integral and so forth. And you have these beautiful Feynman diagrams which describe the scattering amplitude. So we are happy with the notion of quantum field theories and basically the infrared description of effective field theories. And we know what constitutes a consistent quantum field theory or a good effective field theory without gravity. To include gravity and describe it in a quantum theory, we need to couple the quantum field theory to gravity, which means that we need to consider fluctuating space-time instead of fixed flat space. And this is easily accomplished. So whatever Lagrangians you have in the effective theory, we just make the metric. Remember, the metric is not necessarily a background. We add the Einstein term, and we also add the integration in the path integral to the metric degrees of freedom, and that gives you coupling of the background to the metric. And so now we have quantum gravity coupled to the effective theory. It turns out that this approach does not work. And in fact, this was known already a long time ago. The infinities appearing in the Feynman diagrams are incurable, as Feynman himself discovered in the 1960s. The most natural conclusion from this would have been gravity cannot be coupled to quantum fields consistently and should always be viewed only as a background. But this is not consistent in a theory, in a universe we live in, because we both have a different gravity and we also have quantum mechanics. So somehow, something has to give way for these to live together. And so this was left as a puzzle. String theory solves this puzzle and offers a solution by replacing as being fundamental entities, replacing them by extended object, in this case, strings. And this leads to consistent quantum theories of gravity. So the point particles are replaced by strings, and the word lines and the Feynman diagrams are replaced by word sheets and string diagrams, which are these Riemann surfaces where string splits and joins to describe all possible interactions. In a sense, unifying all these Feynman rules and interaction rules into just some simple geometric structure of splitting and joining of strings. So in some sense, it's elegant and unifying. But can we get every consistent quantum theory? Can we get every consistent effective field theory in 4 dimensions coupled to gravity from string theory? Well, string theory comes with 6 extra dimensions, and these should be viewed as compact, tiny spaces, which have so far not been detected because they're small, presumably. And many solutions, however, exist to what the extra compact dimensions can look like. So these are cartoon pictures of what these extra dimensions could look like. It basically is a complicated space, these complicated mathematical objects, 6-dimensional manifolds called Calabi-Yau manifolds feature prominently, and there are many other examples too. They're generally very complicated. And so we take the extended space, multiply by these compact spaces, and typically we expect the space, a fixed, not dynamical internal space. One particular space is frozen in the low energy, and we fix that. And we look at the effective theory we're going to get based on that compact space. So we get some kind of effective field theory, as is always the case. You integrate out the ultraviolet degrees of freedom, and we get some effective theory. In addition, of course, we get an effective field theory with particles and so on, which could be viewed as a particular space of a string, maybe perhaps wrapped around the internal dimensions of string theory. And so we get some kind of effective theory describing interacting particles in the low energy description, and we get some garden variety effective field theory, we would think. For example, if you're interested in 4D, the gauge group SU4 with 2 generations, maybe you choose this particular Calabi-Yau, and a different group with different matter representation might have a different internal space to give you that. And so the natural question will be, okay, suppose I want to have an arbitrary consistent quantum field theory. can I find something here which gives you what I want? So that is the natural question. If this is indeed the case, that if you put something, you get an arbitrary effective theory, then the left-hand side is kind of unnecessary, because you could say, okay, I will just write down anything which appears consistent and I just deal with that. Who cares where it came from? If somebody is interested in constructing the internal geometry of string theory, that's their choice. But as a physicist interested in 4D physics, I don't need to know that. So that would be the attitude, if indeed everything you can get is consistent. It seems that we cannot get arbitrary effective field theories from string theory. And indeed, we seem to obtain only a finite number of quantum field theories from string theory. So this is a surprise. A finite number of quantum field theories which can be coupled to gravity seems to be less than we are learning from string theory. Let me just give you one example of what we find. We find that if you take maximal amount of supersymmetry in 4 dimensions, which is n equal to 4 supersymmetry, the rank of the gauge groups we get in string theory is always less than 23. In particular, if you take a gauge group SUM with n equals to 4 Yang-Mills, m bigger than 23 does not arise in string theory. In fact, SUM for any m is consistent quantum field theory. N equals to 4 Yang-Mills SUM is not only consistent, it is among the most beautiful quantum field theories in 4D. They are finite. They're nice properties. People know a lot about these field theories from just studying various aspects of it, including holography. However, if you want to couple these theories to 4-dimensional quantum gravity, if the rank of the gauge group is bigger than 23, there's zero realization of that in string theory. And we have now arguments which says why, that indeed any theory with rank bigger than 23 is inconsistent, cannot arise as effective field theory, despite the fact that the effective field theory of n equals to 4 Yang-Mills is even finite. There's no problem with the quantum field theory itself. So in fact, it seems from this example that a generic consistent quantum field theory cannot be consistently coupled to gravity. In the case of n equals to 4, if you tabulate the set of all gauge groups allowed, for example, if you take all the SUN gauge groups, you're just getting a finite list. So the probability of a given theory to arise in effective field theory is almost zero, because the numerator is finite and denominator of all possibilities is infinite. So you not only get a finite thing, you actually get a measure zero of allowed of the would-be theories are actually arising as a consistent theory in the infrared of quantum gravitational theories. This raises 2 questions. Does the fact that most quantum field theories do not arise in string theory a deficiency of string theory, or a general consistency about consistency requirements of coupling to quantum gravity, which is related to Cliff's question? Is it because string doesn't give you more, or it's just like it's not possible? So evidence is emerging that this is not a deficiency of string theory, but subtle reasons for consistency of quantum gravity. For the specific case of n equals to 4 Yang-Mills, we have arguments independently of string theory, which uses some of these general features of consistency of quantum gravity to argue for it. So connections with basic facts of quantum gravity, such as unitarity and quantum consistency of black holes, are some of the cornerstones of these kind of arguments which are beyond string theory. And then this raises the broader questions are what criteria distinguish a good effective field theory, part of the string landscape or quantum gravitational landscape, from bad ones, which we call Swampland. So this is part of what's called the Swampland program, figuring out what kind of things are no good, what are the criteria which cannot arise in a consistent theory of quantum gravity in the infrared. So if you think about the spaces of possible quantum field theory and the ones that actually arise as, with having a UV completion, they are kind of a finite jewel in the set of all possibilities. So if you think, for example, as this the green space here as the space of all possible consistent EFTs, then the only ones that arise from consistent quantum gravity is expected to be some small island, some jewels in this subspace. And presumably, of course, one of it is the model we live in. So the landscape is a tiny portion of the effective field theories. And this actually raises the question. You see, many of the questions on effective field theories that has hit the particle physicists is the issue of naturalness. How do you explain this fine-tuning or that fine-tuning? How do you explain the hierarchy and so on? Well, this is because you assume the prior is that all this green space is allowed, and you find sometimes you're in a particular corner and you're trying to explain it. If that particular corner is related to consistency of quantum gravity itself, then it's the prior is not, there's no need for fine-tuning. You will be automatically in that subspace. And so even though it might appear to be fine-tuning from the bigger set of effective field theories, but with the correct prior, which means consistency of quantum gravity coupling, then there's no puzzle. So this actually repackages what should be viewed as hierarchy problem or fine-tuning, more broadly fine-tuning problems in EFTs. So here I review some of the proposed requirements for an effective field theory to end up to be in the good part, the landscape of consistent quantum gravities. First of all, the theory should admit no global symmetries. And in particular, any symmetries that you see should be local and gauged. The second one is uniqueness of quantum gravity. Any two potential consistent quantum gravitational theories should be deformable from one to the other with a finite action process. And this is what's called the cobordism conjecture. All gate charges appear in the spectrum. So anytime you have a gate symmetry, all the possible charges that could have appeared actually do appear. It's a completeness hypothesis. The range of fields is finite. The range of fields, meaning if you take, for example, scalar fields, the effective range of them is finite. If you have an effective field theory of scalar fields, then the range of those fields cannot be arbitrarily large. That means effective field theory breaks down if you go farther away in the field range. This is called the duality conjecture. The theory admits light higher dimensional objects. In other words, a consistent theory of quantum gravity cannot be just a theory of particles. You should have a higher dimensional objects like strings. Gravity is always the weakest force. You have various kinds of forces. For example, you can have electromagnetic forces, gravitational forces, and other forces. But always gravity has to be the weakest one. And then finally, there are restrictions on critical points of cases where you have a potential as a function of scalar fields, if the potential is positive. I talk about these restrictions and also its cosmological implications, what is known as the Sitter conjectures. So here I want to describe these swampland conditions in turn and try to review what kind of things, why we are thinking about these being reasonable, or how have we come to believe in these. So to do that, first I review some elementary facts perhaps about black holes. Just recall some facts. So fix a charge Q and a mass M. Then as long as the mass is bigger than charge in Planck units, there's a black hole. There's a solution to Einstein's equation. And there's an extreme case which corresponds to mass is equal to Q. And this is what's called the extreme of black hole. Black holes have thermodynamical properties, as was shown by Bekenstein and Hawking. And in particular, black holes carry entropy. And the entropy of the black hole is a quarter of the area of the horizon of the black hole. Okay, so now let me start with this. And remember that, and I want to remember that black holes, the other thing is that the black holes always decay according to Hawking radiation. And this is generally believed to be the case, except for possibly the supersymmetric ones, the ones which are protected by supersymmetry. We expect all black holes to disappear. So this is the first criteria for the swampland that I mentioned, that there should be no global symmetries in the consistent theory of quantum gravity. So if you take a black hole and if you throw a charge, a globally conserved charge Q, if you throw it inside the black hole, then since it was a global charge, there will be no remnant of that charge outside. And in particular, there is no electrical field or any field emanating from the black hole to signify that there's a charge inside. So from the outside, there's no difference between this state of the affairs with having somewhat maybe more mass, but no extra charge because it's not measurable from outside. And so when this evaporates according to Hawking radiation, it will emit equal amount of positive and negative charges of that global symmetry because there's no electric field to guide the the radiations in any particular way, and therefore this would lead to the lack of charge conservation. So the evaporation of the black hole is a mechanism. Throwing the charge in the black hole and the black hole disappearing is a mechanism that shows that global symmetries could not have been conserved. This is not a new argument. It predates string theory, perhaps, and it's not. It's kind of it's a kind of a natural thing, and we have seen, of course, this is verified in all the examples we know of string theory. The second thing is uniqueness of quantum gravity. And this uniqueness is, in a sense, a generalization of the no global symmetries conjecture. So any consistent quantum theory of gravity can be deformed to any other through a finite action physical process. In the context of string landscape, if you restrict your attention to the quantum gravities that we get from string theory, the internal geometry of string theory, compactifications, you could have different topologies. Like if you take two different manifolds, M and N, they could have different topologies. Here, what you find is that from these cobordism conjectures is that there is an action principle. There should be a process in which you can go from one manifold to another with finite action. Now, this might sound surprising because M and N might belong to different cobordism classes in terms of topology. So they may not be possible to connect them with the manifolds in a smooth way. But what this conjecture says is that quantum gravity should force to have configurations, albeit perhaps singular, but with finite action, which allows you to go from any one to any other one. If it wasn't the case, then you could give labels or charges associated to a given space, and that would kind of give you a stratification of the space by charges. And it's kind of like a definition of a global symmetry, but more generally a higher form symmetry. So this is kind of a natural extension of the no global symmetry hypothesis. The third criteria is that all charges that can appear in a spectrum of effective field theory should appear. Of course, suppose we have a U1 gauge symmetry and all integral charges Q are in principle allowed to exist. Are there such states in the theory for all charges? Well, without gravity, there's no a priori reason for this. For example, you can easily consider a U1 Maxwell theory with no charge states at all. Pure Maxwell with nothing charged. But this cannot be the case if you have gravity in the story. In fact, if you consider, as I mentioned already, if you have a black hole, for a mass bigger than charge, you can consider a black hole, and the event horizon of it captures the number of states that have the mass m and charge q. So you can take a big black hole for which this formula you trust. If this horizon is big enough, like bigger than Planck's scale, you trust these infrared computations of Hawking in particular, and you find therefore that the number of states grows. There's a huge number of states in your theory of a given mass and charge given by these quantum numbers. But as I said, every charge can appear. So therefore, if you say, okay, this will only appear maybe for large charge because it's macroscopic, you can take a big charge, Q+1, and another black hole with a negative charge Q and collide them. And then by charge conservation, you find that you're left with charge 1, and therefore every charge is appearing in your theory. So the spectrum is complete. So the next criteria I want to discuss is the finite range for fields. So if you have an effective field theory, and if you consider some field in that effective field theory, without gravity, there's generally no problem with having an effective field theory which is valid for arbitrary field range. Phi goes from -infinity to +infinity. But with gravity, it seems that the range of this field for a given effective field theory description is finite. And in particular, for 4D theory, if you're talking about it, the range of the scalar field is order 1, is bounded by order 1 number in Planck units. So the effective field theory must necessarily break down. Now, for this one, we don't have a direct argument from black hole physics yet. We have been trying to understand why this arises, but why do we think this is true? It is basically the bread and butter of dualities in string theory. This is the basic discovery of duality symmetries in string theory is always a manifestation of this property. Namely, the following thing happens. If you consider the space of your scalar fields, so you have a complicated space which parameterizes scalar field space with some kind of an effective action for these scalar fields with some metric on the field space. So you can think about this geometry of this field space. Sometimes in string jargon, we call this the moduli space. So if you look at this geometry of this field space, it's very complicated, but it turns out that what happens if you start somewhere in the middle of this space, if you go far enough away, what happens is that your description of the effective field theories, which was valid here, breaks down as you go to these far away distances. So the middle of it is something like order 1 in Planck units. And when you go away, farther away, a dual description takes over made up of light particles with masses which scale down, which goes down exponentially with mass. So you get mass of states which go like e to the minus some constant times phi. And so far away, power of these light states, which constitutes a weak coupling dual description of the theory. And you have all these different regions that you go to. So always in string theory, we have seen that whenever you go to far enough distances, there will be some dual descriptions taking over. So this is a distance conjecture, namely at large distance in field space, you get a light tower of particles, which means that if you had a cutoff and you had ignored these states far in the middle here, your effective field theory breaks down because these light states emerge and you have to incorporate them. And the statement is that there is no completion of the effective field theory with finite number of degrees of freedom to incorporate all these states everywhere in the theory. In other words, you cannot have an effective field theory which describes all these corners in any particular way. So the notion of the effective field theory breaks down. And this is the basic feature. So in other words, we are seeing we have to kind of embrace as a principle incompletion of the effective field theory as a paradigm for quantum gravity. It is not a bug, it's a feature. If somebody tells you, well, I don't have the full effective field theory, I only have it in this range, you might say, well, sorry, I don't like that. Well, that is a feature, we believe, of quantum gravitational theories coupled with scalars. Completeness of a given effective field theory, it doesn't work. It's in some sense like coordinate patches of a manifold. You can cover a manifold with different coordinate patches, but you cannot have generally one patch which covers everybody. And that's what's happened. So let me talk about the potential application of the distance conjecture. And this is to the cosmological constant. I mean, we believe that we have measured the positive cosmological constant, which is approximately constant, at least, maybe exactly constant, but at least approximately constant. And we can parameterize, it turns out, we can argue that the correct parameterization of the distance for the value of the cosmological constant is exponential in terms of field due to the way it appears in the action. And so therefore we parameterize lambda as e to the minus phi. In units of order 300 is the value that our current lambda has. This is already kind of a large value, if you wish, think of it that way. So you would originally, you would be naturally inclined to think that we already have to have a kind of a tower of states because this is a large value. And so therefore the effective field theory cannot be complete. There must be a tower of states of the order e to the minus a constant times phi, which means in terms of the cosmological constant that you're expecting a tower of states whose mass scales like lambda to some power a, where a is of order 1. For example, this would be an interesting connection perhaps with neutrinos, maybe spheroid neutrinos or other kind of dark matter sector objects, for which the mass goes like lambda to the 1/4. So indeed, this thing which looks very much natural in terms of observation is a bizarre fact from the viewpoint of particle physics. Why should the mass of the neutrino have anything to do with the dark energy? Here, this is beginning to connect them through these kind of ideas. Why the exponent is 1/4, of course, is not explained from this at all. But should be order 1 is not surprising. So let me go to the next criteria, which is that any consistent theory of quantum gravity must have in it extended objects. There must be extended objects, cannot be just a theory of particles. So like M theory, which has membranes, or string theory, which has strings in them. This also follows, at least heuristically, from the previous criteria, the distance conjecture. Namely, start with a given quantum gravity, let's say in higher dimensions, and compactify it on a circle of radius r. You get an effective one lower dimensional theory if you vary the radius, for which the Lagrangian will have an extra scalar field, which has this radius as part of it. And you can see that by going down to the lower dimensional Lagrangian, there'll be an extra term in the action of the form 1/2 grad phi squared, where phi parameterizes its radius in this exponential way. Now, you can ask, okay, so this is a scalar field, but now what about the ranges of it? You could say, well, if the range of this field phi goes to infinity, we should get light states. Indeed, that's the case. If you take phi much bigger than 0, then the radius is much bigger than 1. And indeed, in fact, the example that Cliff already mentioned, you get a tower of KK modes. And the energy goes like e to the minus phi, because the energy scales like 1/r. And so the effective field theory, ignoring these modes, breaks down. However, you could say this distance conjecture is true for any directions you can go. In particular, you can go to negative values of phi. You can go to phi towards negative infinity. This means r goes to 0. So we are saying that the effective field theory should also break down if you shrink the radius to 0. The duality conjecture predicts that something should become light. In fact, many states should become light in this limit. However, how is that possible? You see, if you have a theory of particles, if you go on a circle, if you shrink the circle to 0 size, it becomes just exactly as dimensional reduction, because all the KK modes are becoming heavy, you ignore them, and so you expect that your effective field theory gets better and better. And that is true for particle physics. There's no mechanism in particle physics to get a tower of light states when the radius goes to 0. The only natural mechanism for this to happen is if we have an extended object which feels the global topology of the circle. So if you have an extended object, you can have a circle or a membrane or something whose one of its legs wraps this extra circle. And so when you shrink the radius of circle, the tension or the mass of that object goes down to 0 with it, and you get light states. So this distance conjecture is deeply related to the fact that we need a description of a gravity which is beyond just particles. So the next criterion I want to talk about is that gravity is always the weakest force in the theories of that we have for quantum gravity. In string compactification, it has been observed that whenever we have charged particles, the electric force between them are stronger than the gravitational attraction. So if you have, let's say, two charged objects, the gravitational force m²/r², which is given by this blue arrow here, is typically much smaller than the electric repulsion. In other words, in the Planck units, m should be less than e. The fundamental units of particles and mass of them should be less than their electric charge. And of course, this is true for our universe. The example has mass 10 to the minus 23 with the charge 10 to the minus 1. So indeed, 10 to the minus 23 is not only smaller than 10 to the minus 1, it's much smaller than that. So this weak gravity conjecture is true, of course, in our universe. But why is this a property not just for our universe, but for any putative consistent theory of quantum gravity? Of course, you can easily envision effective field theories that violate this. You can just imagine, just take QED and just crank up the mass of the electron as much as you want. And in that theory, the statement is that this theory cannot be a correct theory of gravity. That cannot be the effective theory of a gravity. So that's already a surprise from the effective field theory viewpoint. So why is that? Well, again, it goes back to the black hole. Black hole plays a prominent role in many of these conditions we are getting. So consider an extremal black hole. So for an extremal black hole, the mass is equal to charge. So generally, mass is bigger than or equal to charge, but for extremal one, it is equal to the charge. However, you can consider, as we have said, Hawking's radiation predicts that these will evaporate by emitting charged particles. So you have charge states Q and states of a charge Q and mass M. So the charge goes down to Q minus Q and M minus M. M is M and Q. The original black hole is big, and you're emitting a tiny small Q and M. So the mass that you're going to end up with should be bigger than the charge that you're left with. In other words, the leftover charge should be less than the leftover mass because of the condition for the black hole. The black hole should always have mass bigger than charge. But we started with Q equals to M. you start with the extremal one. So this suggests that the masses of the entities that you're emitting should include states which has less than or equal to the charge. And the mass equal to the charge can only occur for supersymmetric cases, which are what's called the BPS black holes. Well, this is the kind of arguments that suggest this. Of course, I wouldn't call this a proof because we don't have a proof that the black holes really have to evaporate, especially for the extremal ones. But if it weren't to evaporate, you would have this extreme degeneracy of these states, which is totally bizarre from a field theory perspective, which is possible, but it's very strange. And the only kind of cases where that kind of thing happens is when we have supersymmetric theories. So it's kind of an explanation, even though it's not, I won't call this a proof. There's further evidence for the weak gravity conjecture. So if you take pure Maxwell theory coupled to Einstein's gravity, it leads to naked singularities. In other words, if you try to solve, forget about quantum gravity or anything, just look at classical GR and try to evolve classical GR coupled to pure Maxwell. Then you find that you get by suitable initial conditions, which are nice, you find nevertheless that you can develop strong electrical fields, which lead to violating the weak gravity conjecture. Which violate the absence of naked singularities in the cosmic censorship of the GR that has been suggested. So that has been suggested by Penrose. So of course, even for that, we don't have an argument, but it could be that cosmic censorship is incorrect. But it turns out that weak gravity conjecture actually resolves this problem. You see, first of all, the weak gravity conjecture tells you, or in fact, Swampland conditions tell you that you cannot have pure Maxwell theory. By completeness of the spectrum, as I mentioned originally, there must be charged states in your effective field theory. That's number one. The second statement is that the weak gravity conjecture implies that they cannot be too heavy, these charged particles. Namely, their mass should be less than the charge. So when the electrical field becomes strong, since these are light compared to their charge, you can create these particles out of vacuum and screen the electrical field and try to avoid the singularity naturally, automatically. And it turns out that's exactly what happens. So when you look at these GR situations where it gave you naked singularities, just remembering that there are mass states with mass less than charge, you find that you will never get a naked singularity, and this resolved the conflict between these configurations with cosmic censorship. So as you can see, this criteria is an EFT kind of notion, the IR physics, but somehow you have to append it with this extra data to avoid this singularity. So you can see remnants of these conditions already in the IR in classical GR. If you principles like avoidance of naked singularities. Another application of the weak gravity conjecture to our universe is the following. So if you take the situation we are in, we have dark energy, and so even though we don't know exactly whether our space is de Sitter or not, it's approximately de Sitter because it's approximately constant dark energy, if not exactly. So we are in a situation we have a quasi de Sitter space, and we have positive cosmological constants. Now, evaporation of small and large charged black holes in de Sitter space leads to conditions for the mass. For the small black holes, the condition you get is that there should be charged objects whose mass is less than charge, just like what I talked about already in the previous slide. But it turns out that for big black holes which were almost as big as the horizon of the de Sitter space, you find that there's an opposite direction, that the mass cannot be too small. The mass should be bigger than the charge to the 1/2 times lambda to the 1/4. So in other words, if you view this lambda to the 1/4, if you apply to our universe or dark energy, you find this mass is bigger than 10 to the minus 31 and less than 10 to the minus 1. Mass of the electron is 10 to the minus 23, which of course is in the between them. But I'm using now, we have actually quantitative, quote unquote, quantitative prediction with two ranges, upper and the lower limit, even though it's a little too big for really being too proud of it, but still it fits and it works. And more interestingly, perhaps, is that the left-hand side of this is perhaps connected with the neutrino physics. Unfortunately, of course, the neutrino has no charge, so we cannot directly obtain this bound to say, aha, that means that the neutrino has to have a mass bigger than 10 to minus 31. It's close to it, though, as you can, tantalizingly close, because you could kind of try to see, imagine the neutrinos having some kind of electroweak charge or some kind. So maybe there could be an extension which applies these ideas even to neutrino physics. So as you can see, we are beginning to connect particle physics questions to questions about fine tuning and hierarchy and so on in the context of the neutrino. Of course, if you can kind of explain the neutrino physics in this way, then by the seesaw mechanism for the neutrinos, and assuming the upper scale is close to Planck scale, you already get that the weak scale is somewhere in the middle in the sense that we have already observed, and they're on the Higgs scale. And this will kind of explain a version of the hierarchy problem. So as you can see, these are not that disconnected from issues that are grappling particle physicists in the context of effective field theories and the naturalness issues there. So finally, the last topic I want to cover is restrictions on critical points of cases where you have what are the restrictions on their critical points, as well as how flat can the potential get? So this is an important question for cosmology, both in early cosmology as well as the late cosmology. For early cosmology, for example, in the context of the inflationary scenario, one looks for effective potentials as a function of scalars, which kind of look like this. You have some flat regions, and at some point, some regions where the field can settle onto. And we expect, one looks for potentials for which you have a relatively flat description, so that you can have the inflation, slow roll inflation, and you'll settle into a bottom of a potential somewhere with the value of the potential still positive, which presumably will account for the dark energy of our universe. So that's kind of a simple picture that is what you could call is one of the models for standard cosmology. And you could ask if this is difficult in any sense, and is this consistent with quantum gravity or not? Well, the situation with positive potential is very difficult to probe using string theory, the techniques we are familiar with, partly and mainly, I would say, because supersymmetry must be broken. You cannot have a situation with positive potential and supersymmetry not broken. For negative potential, you can have supersymmetry preserved, like anti-de Sitter space. You can have plenty of beautiful solutions in string landscape involving a negative potential with supersymmetry. But for positive potential, it's easy to argue that supersymmetry must be broken. Okay, so a lot of the techniques that we know in string theory arise from supersymmetric situations. So for non-supersymmetric case, we are on a limb to make predictions. Of course, we can still look at weak coupling regions of string theory. Like you can take the coupling to be weak and then consider non-supersymmetric background and see what kind of predictions that makes. So indeed, for example, if you go back to the space of scalar fields I was telling you about, these regions of weak coupling arise as you go far away in the field space. And in these cases, in these regions, you can actually compute an effective potentials when you break supersymmetry. And you find that the effective potential looks like decaying down towards zero when it's positive, and in fact, similarly when it's negative, but let me focus on the positive one. So you find that the effective potential always goes to zero. In fact, it goes to zero exponentially fast. So you find in particular that the potentials that you get in string theory decay like e to the minus some constant times phi, where if you measure phi in Planck units, the C is order 1. In fact, in string compactifications, there's a general analysis which suggests that this slope, which is this constant C, V prime, absolute value of V prime over V, is bigger than square root of 2/3 when you go at least far enough in field space. At asymptotic infinity in field space, this potential should go to zero faster than exponential with the value square root of 2/3. Now, this already is interesting because this is, even if we don't know much about inside, we don't know how the potential might look inside the field range when you're in the middle of the moduli space, when you're near phi equals 0 here. But But if we want to have a minimum, like a quasi-de Sitter space of some kind, it's not going to be exactly stable. Namely, we have this tunneling possibility because far enough in field space, it's going to go to 0. So already without any further ado, we are predicting that no model of dark energy can be stable. You cannot have a situation where you have potential goes has an absolute minimum at positive value. So we are predicting that, for example, even if we are in a situation with a metastable de Sitter, it is only metastable. It cannot be exactly stable. And therefore, the universe we live in, if it's in any form like this, it has to decay. There's a decay time. Of course, we are not sure if this thing exists. We do not know situations like this where the potential is exactly stable, precisely because we don't have reliable techniques in string theory. As the Sitter Swampland constraint at large fields fits very nicely with the distance conjecture. Namely, here I told you that there's a tower of states whose mass go like e to the minus a phi, and typically you get a potential, let's say in 4D, getting contributions from this tower. And you like m to the 4th. And if you compute that, this gives you like e to the minus some 4a times phi. So you again find that the potential grows exponentially with phi. And this is kind of consistent with the distance conjecture. So this fall off of the potential is kind of related to the distance conjecture, which is also related to the duality conjectures in string theory. And then the question is what happens in the middle, which we do not have any real control over. There are 3 possibilities of what could happen for V inside. One thing could be that there are no restrictions, that anything can go. It's a little strange for this to be the case, given the very specific boundary conditions for the V that we get, which leads to instability. The other 2 possibilities have been suggested. One of them is called the de Sitter Swampland conjecture, which suggests that the V is sufficiently unstable. That is, either V prime continues to hold some kind of a bound, like the slope is bigger than its value, or it is sufficiently unstable. So if you have a critical point, you may be on top of a hill with second derivative relative to V to be much smaller than, which is less than order 1 in Planck units in absolute value and unstable. So it's sufficiently unstable or going like this. So this is one possibility. Another one is what's called the Transplanckian censorship conjecture. So the motivation for the Transplanckian censorship conjecture is the following. If you consider a universe which grows from, which is growing, you want to have a situation where the sub-Planckian modes do not get bigger than the horizon at any time. Because if it gets bigger than horizon, it kind of gets frozen in. And you would expect that the sub-Planckian modes are non-physical. And so they're being frozen is a little strange. There's no proof of that, of course, but if you actually assume that there cannot be any putative universe for which the final over initial radii times the L Planck, the magnification of L Planck, could lead to the horizon size of the final state, it turns out that using just this criteria, you obtain the bound that was obtained that I showed for you previously, namely the slope of the potential ends up being always bigger than square root of 2/3 at asymptotic infinity. So you can derive this value. So this square root of 2/3 can be obtained from simply this condition. The square root of 2/3 is obtained in string examples and seems to be perfectly consistent with this conjecture. We don't have any first principle derivation of this conjecture either. That's why it's still called conjecture. But still, it's quite amusing that it explains, at least asymptotically. The Transplanckian censorship does allow critical points, stable critical points in the middle, as long as they are not too stable. They cannot be too stable. Because if they are too stable, then the universe expands, and after a long enough time, AF over AI will overtake the horizon, and that would be impossible. So what that means is that if you have so the Transplanckian conjecture suggests that even if you have a de Sitter or quasi-de Sitter space, it better be that its lifetime is not much bigger than the natural scale given by the horizon of the de Sitter. So then let me just continue here. So let me just then connect the Swampland conjectures on inflation. So inflation is not ruled out by these conditions, but it seems to be strongly fine-tuned in many ways. And the duality conjecture leads to predictions that we cannot have naturally arbitrarily large field inflation because we get a tower of light states. So multi-field kind of inflation may overcome this, but it's still a bit difficult in very many of these models for inflation. Another thing is the slope conjecture. For example, the plateau models will give you C, the V prime over V to be less than 0.02, which leads to rather small numbers. And for the slope, which is possible, but still small, if you believe in the Sitter conjecture, or if you believe in the Transplanckian conjecture that I was mentioning, you end up that the Transplanckian conjecture has strong problems with high energy inflation. So the inflation potential is going to be low energy in the sense that it should be bounded by 10 to the 9 GeV, the scale of the inflation. And this leads to things which are very fine-tuned, where epsilon 10 to the minus 31 or r is 10 to the minus 30 for these slow roll parameters, and the r parameter of the inflation, which means basically that the tensor modes are absent if this is the case. But these are all very highly fine-tuned, and these suffer from initial condition problems in inflation if you go there. So I would say that inflation not ruled out, but looks very bizarre if these conditions are correct. Puzzles of early universe arise after one makes, so you might ask, what happens, what replaces inflation? What explains the success of inflation? What other model can explain it? And many puzzles of the early universe arises after one makes a major assumption, which is at odds with what we know in string theory and dualities. The main assumption is that we are trying to solve a problem of what happens to the effective field theory that we know is correct today when you go back in early times. So in the early times, you're getting to the extreme limit of infinite distance. The temperature is going to infinity, the radius of the universe is going to 0, and these are infinite distance in field space. So therefore, the dualities or the distance conjecture in string theory tells you you should be expecting a tower of states. Your effective field is going to have to break down. The usual attitude of effective field theory is to add one or two fields to fix the problem. For example, add an inflaton field, add the potential. Here we are saying that in the context of string theory, that's not natural. We are expecting to have the full breakdown of the effective field theories, not just by one field or more, or two, but actually the whole tower of particles coming light and ruining the whole description. So we expect a dual description to take over. And so this would be, so the picture would be that our universe emerged from a dual picture, for example, like in the string gas cosmology and so forth, and not in a picture involving just one or two additional fields like inflaton. So let me say what we expect from these pictures for the present and the future of cosmology in the context of Swampland. If we assume the de Sitter Swampland conjecture, we can only be in the rolling potential situation. And you can see that moreover, in a short time, we will roll more than the Planck units. So therefore, since you have to get light states when you roll too much, it gives you a bound on the lifetime before you enter with your effective field theory should break down, before you enter a new phase of our universe. And that lifetime, when you use the observations, you fit with the observations, gives you, it's like 30 times the current age of the universe. If you assume TCC, you find a bound on the age of the universe, which is the Hubble scale, 1 over root lambda, times the log of 1 over root lambda, which is about 2 trillion years. So in either case, you're getting a bound which is of the order of tens or hundreds times the age of the universe, but not much more. Either of these de Sitter conjecture explains at least one version of the coincidence problem, is that why the scale associated with the measured value of the dark energy is close to the current age of the universe. In fact, the picture would be that in any universe where the dark energy is measured, and in fact, if it's a sizable fraction of the universe's energy budget, the time scale associated with that dark energy is the same as the age of that universe. And because it could not have been discovered much later, the universe is about to decay and disappear altogether. So this explains why we live in an age of the universe which is not too far from 1 over root lambda. So let me conclude by saying that the Swampland conditions can lead to potentially observable consequences for particle physics and cosmology. Almost all quantum field theories are in the Swampland. This is a good thing because it limits a lot of the issues that we are facing with fine-tuning problems like hierarchy, and may end up having different solutions, and it puts clear restrictions on consistent quantum gravitational theories. These ideas suggest that restrictions on light matter fields exist. For example, I was giving you some examples like neutrino physics or mass of the electron. And moreover, the positive energy in the context of quantum gravity lead to local and global instabilities, and this may explain the a version of the constants problem. New ideas, dualities of string theory, for example, are expected to play a role in early universe. Thank you for listening. Point off.